well, here is why wave functions collapse in Bohmian mechanics. Okay, so here's a particular example. What I'm showing here is configuration space of a particle and a detector. The particle, of course, has 3 dimensions, moves in 3 dimensions, and the detector has 10 to the 23 particles. So in the configuration space of the detector, it actually has 3 times 10 to the 23 dimensions, of which I'm drawing only 1. So, okay, so this picture is kind of schematic. Okay, so there are really many dimensions here. And what I'm drawing is the significant support of the wave function. By this, I mean the following. I mean that in these 2 regions here, these are the regions where psi is significantly non-zero. And outside of these 2 regions, everywhere else in the configuration space, psi is very close to 0. So we neglect that. Okay, so here I'm considering a situation at the beginning of a quantum measurement. The quantum measurement here would be a position measurement. Let's say for the particle, we have a superposition of position in this region. Now I should show it on the axis, right? Because I'm talking about the position of the particle. So here would be one region for the particle. Here would be a different region. Okay, so we have a superposition of 2 different locations or 2 different regions for the particle. And now let's say we have a product wave function, 1 factor for the particle, 1 factor for the detector. So if you think of vectors like Gaussians, then you know that when you take the product of 2 Gaussians, you have a Gaussian again, and the level surfaces of those Gaussians would be ellipsoids, or in this picture, circles. Okay, so here we consider a particular example case in which we have a spatial superposition. And now we let that evolve with time. Okay, now as time evolves, the particle, or at least the part of the wave function that's in this region, let's say this is the region where also the detector is. And if the particle is here, then it interacts with the detector. And the interaction with the detector will have the consequence that the detector somehow changes its states, that some of the particles in the detector go to different places. So for example, if the detector is triggered, then there's a current, an electric current of going off in the detector. So some millions of electrons go in a macroscopically different place. Okay, that's why this I'm sorry, why this wave packet is moving upwards. So the right wave packet is moving upwards. That represents the interaction between the particle and the detector. The left wave packet does nothing because there the particle is far from the detector. There's no interaction between the detector. So the detector remains in its ready state. Okay, so now we've arrived at the wave function of the composite system of particle plus detector at the end of this measurement process. Okay, so we have a wave packet in the in the southwest corner and a wave packet in the northeast corner. The wave packet in the southwest corner corresponds to no detection, and the one in the northeast corner to a detection has occurred. Well, that is the kind of the quantum state. It's a quantum state of the detector in which the detector has been triggered. Okay, now what happens is, so far I've drawn what happens to the wave function. Now what happens to the Bohmian trajectories? You know, now there's a Bohmian configuration for the particle, and there's a Bohmian configuration for the detector. The detector itself consists of electrons and quarks. And like all other electrons and quarks, according to Bohmian mechanics, it has particles. So the particles move around. So that means that somewhere in this configuration space, at each time, there's a point where the actual configuration the actual Bohmian configuration, the configuration of the Bohmian particles actually is. Now, at each time, it's chi-square distributed, but that doesn't tell you how it changes with time, but Bohm's equation of motion tells you how it changes with time. And let me go back in this little movie. So at the time, okay, for some strange reason, it's called t equals 5. And this, okay, that's the beginning of this experiment. Okay, so the configuration, let's say if these two packets have equal size, then there's a 50-50 probability of the actual configuration being in the left packet or being in the right packet. Now, when you think about it some more, try to analyze the situation, what happens is that the Bohmian configuration will actually follow the wave packet. So at the end of this experiment, then the Bohmian configuration will still be in one of the two packets. And now, if it happens to be in the northeast packet, then the configuration of a detector is a configuration in which the detector has clicked. Let's say maybe the detector, some current goes through some wires, maybe if you have some measurement apparatus, maybe a needle goes to a different position. So this is the ready state. And then if it detects the particle, then it goes to a different, or maybe some printout, some ink on paper says particle was detected over there. Okay, different configuration. If you look at the configuration of the Bohmian particle, then you have the outcome, the particle has been detected. That's because the actual configuration is in this northeast packet. Okay, so here's the situation. The actual configuration lies in one of the packets, let's say the upper one, the northeast one. Now, if that is the actual configuration, then that means, let me go back one slide, that the Y configuration, the configuration of the detector, lies in this region here. So Q2 is the same as Y. Okay, so the detector configuration lies in this region. Good. So that means when you form the conditional wave function, let me go back to the definition of the conditional wave function. You take the full wave function, plug in the actual configuration of the environment. So what do you get? So at some point on here, that's the actual configuration. So you consider a cross section of this picture here. And since the southwest packet does not intersect this horizontal line, which corresponds to this capital Y, the conditional wave function contains only this part of the wave function. That is, psi has collapsed. The lowercase psi, the conditional wave function. Let me show you again. At the initial time, the capital Y was over here, and the conditional wave function cut through both wave packets. So the wave packet of the particle, the wave function of the particle, had these two contributions in two locations, and at the end of the experiment, it only has one contribution. It has collapsed. Moreover, decoherence occurs. For our purposes here, decoherence means the following. The two packets of psi do not overlap in configuration space, and they will not overlap anymore in the future, at least for the next 10 to the 100 years. And this always happens with macroscopically different packets. Let me explain. So here are two regions in the detector configuration space. Okay, these two regions are macroscopically different because a macroscopic number of electrons has moved in a different location, or the needle of this apparatus has moved in a different place. Now, whenever you have such a situation that two regions in configuration space are macroscopically different, then it becomes very difficult to make two wave packets that are localized in these regions overlap again. because then you would have to bring back 10 to the 23 particles to exactly the same configuration again for making these wave packets overlap. So for example, if if you consider two configurations of the apparatus with two different needle positions, then air molecules will bounce off the needle, and some air molecule will bounce off that would not have bounced off if the needle had been in a different location. So now, in order to bring everything back, you would have to catch this molecule, bring it back, bounce it back, so you can make sure there are no degrees of freedom that contain any traces of what the needle position was. So that's why it becomes very difficult. That's the essence of decoherence. And for our purposes, the important consequence here is that these two wave packets that you see in the picture will not overlap again in configuration space, because the configuration space is really a configuration space of 10 to the 23 dimensions, okay? And you can't get them to agree in all these 10 to the 23 variables. Good. So now, if they will not overlap again in the future, then as a consequence of that, the actual Bohmian configuration will be influenced, will be guided by just this northeast packet. And the existence of the southwest packet, which is still there, actually doesn't influence the motion of the actual particles. It would influence as soon as these two packets overlapped again, as you saw in the double slit experiment. Okay, so as long as you try to calculate the motion of the particles, you can also forget about the southwest packet. And in particular, as far as the conditional wave function is concerned, it will only be a cross-section through this packet and will not intersect the other packet anytime in the future for the next 10 to the 100 years. Not forever, okay, kind of theoretically, there are times, very late times at which they will overlap, okay, but it's not of practical relevance. So that means psi collapses and psi stays collapsed. The lowercase psi, I mean, the conditional wave function. Okay, so here I expressed it as follows. The lowercase psi will follow the upper packet for the next 10 to the 100 years. So that was a particular example of a measurement process where the initial state was a spatial superposition. Let's look at a somewhat more general state, kind of not position, arbitrary observable. Okay, consider an ideal quantum measurement of the observable A, arbitrary, self-adjoint, but let's say with discrete spectrum. So alpha are the eigenvalues, P alpha the projections. Now let's say the measurement process begins at time t0 and ends at time t1. At t0, the wave function of object and apparatus together is this product. Okay, it's disentangled, a tensor product, which means it's the lowercase psi. Oh, the lowercase psi now at this point means not the conditional wave function. It means the wave function of the object that we put into this measurement process. And what's the lowercase phi? That's the ready state of the apparatus, the wave function of the apparatus at the initial time of the measurement experiment. Okay, so now this is the full wave function. Now the full wave function evolves according to the Schrödinger equation. So I wrote it down what it is. Okay, good. So that's the Schrödinger equation in 3 times 10 to the 23 variables, okay, or more than that. Good. So I copied again here. Initial wave function of the measurement process is this product, and the final one is whatever this product evolves to under the Schrödinger evolution. Okay, now in order to see what's happening here, let's first consider a special case, namely the special case that the object is in an eigenstate of A. So we assume now that this state lowercase psi, the state of the object that we put into this measurement process, is an eigenvector of A. Then we would hope that the measurement process yields the value alpha which is the corresponding eigenvalue. Okay, so putting this in, we evolve it up to time t1. So we have the wave function at t1 under the condition that we put in an eigenstate with eigenvalue alpha. That's called the result, a wave function of system and of object and apparatus together, psi alpha. Now, since the outcome should be alpha, this psi alpha should be a wave function that represents an apparatus that displays the value alpha. So if the apparatus has a needle, now the needle will point to the value alpha. Okay, now suppose next we choose an arbitrary wave function for the object. Okay, a superposition. So a general wave function is a superposition with non-trivial coefficients C alpha. So the C alpha here are complex numbers. They're the coefficients of the different eigenstates. By non-trivial, I mean they're not all but 1, 0. Okay, so the psi is not just one of these eigenstates. Say at least 2 of them are non-zero. Okay, then it follows by the linearity of the Schrödinger equation that the wave function at time t1 is the same superposition of the psi alphas. Let me say that again. So at t0, the wave function of object and apparatus together then is this expression. Okay, it evolves to this thing, which is a superposition of wave functions of apparatuses displaying different outcomes. Okay, now, okay, so here I have a picture of that. So again, here's the object, and here's the apparatus. So now this is my, at time t0, my product wave function. So this should be closed here. It's just a bad way of drawing. Okay, so this now evolves in this way. Contributions with different eigenvalues now move to different regions of the configuration space. So here's the region of the Y configuration space in which the needle points to a particular alpha value. Here's a region in the Y configuration space where the needle points to a different alpha value. So the wave function is a superposition of these 2 or more contributions. Okay, now in Bohmian mechanics, the capital Y, the actual configuration of the apparatus, provides the actual position of the needle and thus the actual outcome. The actual outcome, capital Z, here will be the appropriate function of the configuration of the apparatus. Okay, now the probability that this has the value alpha from the equivariance theorem, which says at every time the configuration is psi squared distributed, is the probability for this outcome here is you have to take this part of the wave function, this packet here, integrate psi squared over this region. Okay, so this is the same thing as the norm squared of the psi alpha. Psi alpha is just this packet here, and norm squared is psi squared integrated over this region. And then simple computation shows that this is the same as the absolute square of the coefficient C alpha. And that agrees with the rules of quantum mechanics. This is exactly what Born's rule for arbitrary observables said. And if that is the case, that the outcome was alpha, then and if moreover, let's assume for simplicity that that this measurement process does not change the eigenstate of the system. So if the system was in state lowercase psi alpha, then also at the final time of the measurement process, it will still be a product between psi alpha and some state of the apparatus that I call phi alpha. That is the state of the apparatus where the needle is pointing to the value alpha. Okay, but the state psi alpha then of the particle has not been, of the object or the system has not been changed relative to what it was initially. Then it follows that the conditional wave function is just this psi alpha, this eigenfunction at the appropriate value of alpha, which is the alpha that came out as the result of the experiment. Again, so we see that the wave function has collapsed in agreement with the collapse rule of quantum mechanics, also for arbitrary observables. And moreover, by decoherence, it will stay that then over time, it will not kind of go back after a second to a different wave function. So from that point onwards, for all practical purposes, you can just replace the wave function of your object by the corresponding eigenfunction, as was claimed in the rules of quantum mechanics. Now, there's a surprising consequence of that. Or maybe surprising, maybe you're not surprised. Okay. The consequence is that Bohmian mechanics actually makes the correct predictions, makes the same predictions as you have in the usual rules of quantum mechanics. Or, as I wrote it here, observers inhabiting a Bohmian universe, which is a hypothetical universe governed by the laws of Bohmian mechanics. And these observers are, of course, themselves made out of Bohmian particles. They consist of Bohmian particles. So observers inhabiting a Bohmian universe, they observe random looking outcomes of their experiments whose statistics agree with the rules of quantum mechanics for making predictions. In short, Bohmian mechanics is empirically adequate. Why should you be surprised? Because normally you say, oh, you can't have trajectories. If you introduce trajectories, you get to wrong predictions. You see, it's actually not true. You have to do trajectories the right way, the smart way, the Bohm way. Then you don't get wrong predictions. Bohm makes the right predictions. Okay, so various people have claimed that it is impossible to have any theory like Bohmian mechanics. So here's a quote from Werner Heisenberg, writing in 1958. We can no longer speak of the behavior of the particle independently of the process of observation. Or the idea of an objective real world whose smallest parts exist objectively in the same sense as stones or trees exist, independently of whether or not we observe them, is impossible. Well, Heisenberg was wrong. Okay, we know now that Bohmian mechanics is a counterexample to this impossibility claim, that it actually is possible to have a theory postulating an objective real world in which certain things move around in certain ways, and which has the consequence that you observe exactly what quantum mechanics predicts. Now, there are perhaps several things that you may find surprising about that. For example, what about Heisenberg's uncertainty relation? Didn't you think that, okay, you can't have trajectories because of uncertainty? For example, if you have a trajectory, then you have a definite position. So the position uncertainty is 0, and then the momentum uncertainty is infinite. But in Bohmian mechanics, you have a definite position and a definite velocity at the same time. So isn't that in contradiction with Heisenberg's uncertainty relation? The answer is no, it's not. Here's why it's not. Here's what the uncertainty relation actually says in Bohmian mechanics. It says, whenever the wave function is narrow, so that the uncertainty about the actual position is small, that is, whenever we know the actual position to a high degree of accuracy, then there's a big spread in Bohmian velocities. And you can actually see that in this picture here of the double slit experiment. You see here, the wave function passes through a slit, okay? And the slit is narrow. So the slit forces the wave function to be narrow, okay? So half of the trajectories, they pass through the slit. So you know the position at the instant when the passage through the slit occurs, you know the position very precisely because the slit is narrow. But then the velocities, I mean, each trajectory has just one definite velocity, but since you don't know which trajectory it is, you have a full collection of different possible velocities. You see in this picture how the velocities spread, they go apart in different directions. Okay, so if you don't know the exact position of the particle in the slit, and you don't know it, then you don't know what the exact velocity is. Okay, so that's what Heisenberg's uncertainty relation says for Bohmian mechanics. How can Bohmian mechanics be compatible with non-commuting observables? Where non-commuting observables be thought of as the kind of something that really shows us that you can't do with trajectories? Well, you've seen that Bohmian mechanics actually gets along well with arbitrary self-adjoint operators. Okay, so we know for a fact that there is no such conflict. And when you think about where does that come from, it's essentially because different choices of the ready state phi of the apparatus lead to different kinds of interactions with the object. We'll see a concrete example of that in lecture 3. Okay. A short remark on the history of this idea of Bohmian mechanics. Already in 1924, Einstein toys with the idea that photons may have trajectories obeying an equation of motion similar to that of Bohmian mechanics. The idea that somehow the electromagnetic field, which we would now call the photon wave function, somehow guides the photon trajectories. And John Slater worked with him on that, but he didn't have actually a good proposal for what the equation of motion would be. He had a proposal which was essentially the Poynting vector, but actually that's not a good proposal. Shortly afterwards, Louis de Broglie actually discovered Bohmian mechanics. He called it the pilot wave theory. In 1945, Nathan Rosen, the R of EPR, independently discovered Bohmian mechanics. And in 1952, David Bohm independently discovered Bohmian mechanics. He was the first to realize that the theory is empirically adequate. All of the others, Einstein and de Broglie and Rosen, came to the conclusion that the theory somehow makes wrong predictions, but they all made mistakes. It actually makes the correct predictions. And Bohm was the first to realize that. That's why we call the theory now Bohmian mechanics and not Rosen mechanics or de Broglie mechanics. Okay, so let's see. That's the last slide of what I planned for lecture 1, but we still have a few more minutes. So I would already start with my slides for lecture 2, unless you have some questions at this point. Okay, then let me move on. Oh, yes, please. Okay. Okay, so if you have a question, just open your microphone and interrupt me.
Can I?
Sure.
So, in the case of electron, it was kind of simple because we kind of knew what the fundamental degree of freedom was, right? So, in quantum mechanics, you know, there are kind of examples where like the dynamical degrees of freedom can change, or you know, maybe the electron's really composite.
What do you have in mind? Can you give an example? What do you have in mind?
So I've read if you have an atom in a cavity,
mm-hmm.
So that the photon is kind of in the cavity as well, you can have a superposition where, say, the electron, you have like a superposition of an electron in excited state and a de-excited state and a photon emission, or a photon in the cavity.
Mm-hmm.
Or maybe this is not so good. Well, let's say in all say phase transitions in like superconductivity, then you have, maybe that's not such a good example because you still have electrons in the fundamental degrees of freedom. But then kind of the things that carry charge no longer become spin half things. So there you have kind of, yes, yeah.
Yeah, maybe I can make a few remarks. I'm not sure whether they would really answer your question, but maybe after these remarks, then you can maybe tell me whether that helps. Okay, so a first remark would concern the creation and annihilation of particles. Okay, so the configuration space, script Q, so far I assumed a fixed number of particles. Somehow my pen doesn't work perfectly. Okay, so that would be R3N. Now, if you have a theory with creation and annihilation of particles, then you could have configurations with different numbers of particles, and the number of particles could change over time. So then this thing here would be the appropriate configuration space, which is kind of the analog of Fock space. Well, what Fock space is for Hilbert space, this thing here is for a configuration space. Okay, it's the configuration space of a variable number of particles. This space looks like this. So for n equals 0, you have just one configuration, which is the empty configuration. Now for n equals 1, you have just R3. Okay, I will draw it for one dimension. Okay, now for n equals 2, you have R6. Okay, in one dimension, it would be R2. So I draw something two-dimensional. And then for 3 particles, okay, you get higher dimension and so on. Okay, so now if in Bohmian mechanics you wanted to include particle creation and annihilation, then you would say, a natural approach at least would be to say this, okay, you have the actual Bohmian configuration that moves around in the configuration space. So it's somewhere, it has some definite number of particles, but then maybe at some point, a new particle gets created, say an electron emits a photon, and then you would jump to a different sector in configuration space and then continue moving around there. Okay, and at some other point in time, an electron might absorb a photon, so the number of particles might jump down again. So you would, from this configuration, you would jump to that configuration and then move on there. Okay, so then psi would be non-zero over many of these sectors. The psi-square distribution would be a probability distribution not only over positions of particles, but also over numbers of particles. And your Bohmian trajectory would then include jumps between different sectors. That's just because, well, you can't get from one sector to another sector without a jump. Okay. So this is one remark about what particle creation can look like in, in Bohmian mechanics. So maybe that is helpful. Let me make another remark. In Bohmian mechanics, you need to know what kind of ontology you want to have. And this is kind of something that, that you need to discuss when you set up the theory. So in particular, for quantum field theory, there's the question, for a quantum field, what's the right ontology? Is it a field configuration? Like, is there an actual electromagnetic field, like you have actual positions? Or do you have, that would be called a field ontology? Or do you have photon particles with trajectories? That would be called a particle ontology. So they're kind of, we can imagine two possibilities what a Bohmian theory for quantum field theory could be like. It could have a field ontology or a particle ontology, or maybe there are further possibilities. And now it's not so easy to decide kind of which of them would be the right Bohmian theory. Actually, it's a question that is still debated. It's a question a question of ongoing research, how to extend Bohmian mechanics to quantum field theory, how these things could be set up mathematically, and what consequences that would have, and what kind of advantages or disadvantages that would have. So the upshot here is, I think, maybe the answer to your question is, yes, it's not obvious what the right ontology should be. And one would have to study different possibilities and then try to make a decision which ontology seems more convincing. Okay, so now you tell me whether that answered your question.
I think I understand what you're getting at.
Or maybe we talk about it again in one of the other lectures.
Okay, maybe can I ask just another question?
Sure.
To do with these anti-commuting. Oh no, is it? I can't remember now. So, how does the exclusion principle, the Pauli exclusion principle, manifest itself in Bohmian mechanics?
As follows: as in other versions of quantum mechanics, you would insist that the wave function is anti-symmetric against permutation, or for bosons symmetric against permutation. And then the consequence that you get from that is that the Bohmian velocity vector field in configuration space is actually symmetric under permutation of the particles. The consequence of that is if you change the numbering of your particles, if instead of this being particle 1 and that being particle 2, you say, oh, that is particle 1 and this is particle 2, then you still get the same Bohmian trajectories. Changing the numbering of the particles doesn't change the Bohmian trajectories. For comparison, if you had an arbitrary wave function, for example, for distinguishable particles, then changing the numbers means, now it's not, you've changed the identities of the particles. So first this was the electron and that was the neutrino, and now you change it. Now this is the neutrino and that is the electron. That of course leads to completely different trajectories. Okay, but if they're identical particles, you can change the numbering and you still get the same Bohmian trajectories. So that's good. That's as it should be. In fact, you can go even further and say, well, taking it seriously, the fact that we have identical particles, we should think that in physical reality, there is no difference between particle 1 being here and particle 2 being there, or particle 2 being here and particle 1 being there. So let me write this down. If you have a configuration of 2 particles like this, you should say, oh, it's really physically the same configuration like this. We should identify them. We should introduce an equivalence relation and say it's only equivalence classes. An equivalence class could now easily be characterized by giving the set with these 2 entries instead of the n-tuple. So the n-tuple, an element of R3n, would be an ordered list of particle positions, whereas this would be an unordered list of particle positions. Okay, so instead of...
And then it doesn't exist, simply. It's not...
So here you would have R3n, which is the set of all ordered configurations. And here you have something that is sometimes called NR3, the set of all unordered configurations, which is the set of all n element subsets of R3. Okay.
And this naturally excludes when they're the same, because that set doesn't exist. Because the set kind of the same.
And they're the same
elements.
Okay, so well, it's a set of measure 0 where they're the same. that allows you to mathematically remove that set, or you could also there are also ways of doing it where you keep that set. Okay, so there are different ways of doing that. So the upshot here is, if somebody insists that NR3 is really the physical configuration space, and that actually does seem more natural, then Bohmian mechanics works with that, no problem. You get a trajectory in NR3. So that would mean you don't even have to say which particle you regard as particle 1 and which one as particle 2, I'm sorry. And then you can ask, okay, your wave function, however, would have to be a wave function on R3n. And then you can ask, okay, which wave function on R3n would lead to velocity fields on NR3 that don't depend on your ordering? Okay, and then you find out, okay, so the natural classes are the symmetric functions and the antisymmetric functions. So you could even say, in a sense, that Bohmian mechanics has some kind of explanation why your wave functions would have to be symmetric or antisymmetric. Okay, so the situation is, number one, Bohmian mechanics does work with identical particles. And number two, in a sense, it even has an explanation of why identical particles have to have either symmetric or antisymmetric wave functions.
Okay, that makes sense. Thanks.
You're welcome. Are there other questions? If there are no other questions, then okay. Yes, please.
I'm Kumar. Would you please explain one more time Heisenberg uncertainty principle, the context of Bohmian mechanics?
Could you say again which principle? I didn't hear.
Heisenberg
principle.
Yeah.
Okay, yeah, let me go back to that slide, or maybe let me draw it over here. Okay. So I had this picture with the slit. So the slit makes the wave function very narrow, and when the wave function is very narrow, then we know the position of the particle very precisely, but then the wave function spreads very quickly. Somehow my pen doesn't work well. Okay, and you can, as a consequence of this quick spreading of the wave function, also the Bohmian trajectories, they move apart quickly. So whenever you know the Bohmian position okay, so I should say so nature knows the exact position of the particle, but we don't know the exact position of the particle. We only know that it is psi-square distributed, and maybe we have some reasons for knowing what psi should be. For example, in this situation with the slit, because of the slit, we know what psi should look like. Good, but then we don't know exactly which of these different possible trajectories is the actual one. We can compute all of these trajectories, but we don't know which is the correct one. And then we have uncertainty in the sense of ignorance. We don't know what the actual velocity is. The actual velocity could be near zero, or it could be large and positive, or it could be large and negative. That's what you see in this picture over here. So, okay, in this picture over here. Okay.
Okay, thank you.
Let's stop here.